In today's lecture, we're going to discuss modular arithmetic. So these are operations with remainders. So let's fix a natural number m, which is greater or equal to 2. And we consider the set of remainders after division by m. So that set we are going to denote Zm. So the possible values of remainders are 0, 1, 2, and all the way up to m minus 1. So m minus 1 is the highest possible remainder when we divide by m. So let's discuss the operation of division with remainder. So what does it mean? So when we want to find the remainder of an integer s after division by m. So what do we actually do? So what we do is we write s in the form, we take a multiple of m plus whatever is left is a remainder. Right? So if s is positive, then we can repeatedly subtract m from s until we get the result which is strictly less than m. And so when we do this, we get that the value of r will be between 0 and m minus 1. And so d here is an integer. So this applies not only to positive numbers, but also to negative numbers. Right? So as an example, so let us look at what is remainder of negative 2 after division by 7, or we're going to write mod 7. So when we write mod, so this indicates that we are dividing by 7 with the remainder. So in this case, so okay, when s is positive, we subtract multiples of m. And when s is negative, like negative 2 in this case, then we add multiples of m, or 7 in this particular case. So what we can do, in this case, we need to add just 1, right? So 7 times 1. So, and the result is 5. And so here this conforms this form of writing. So equivalently, we can write negative 2 as 7 times negative 1 plus 5. All right, and in this case, so d is negative 1, and r is equal to 5. When we deal with remainders, it is helpful to make the following observation. That two integers have the same remainder mod m if and only if their difference is divisible by m. Like in this case, so here we're saying that negative 2 and 5 have the same remainder after division by 7. And indeed, what's the difference between 5 and negative 2? So 5 minus negative 2, that is 7. Right? So this means that the difference between these two integers is 7, so they have the same remainder mod 7. Let us now discuss addition and multiplication of remainders. So here we formulate the following rule. So to add or multiply two remainders, take any pair of integers with these remainders, add them or multiply them, and take the remainder of the result. Now, let's compare it with another rule that we discussed last time. So last time we said the following. So to add or multiply two remainders, add or multiply them and take the remainder of the result. So it seems that our first rule was simpler, right? Yet, so today we're going to adopt the second rule. So let us see what's the disadvantage of this rule, simpler rule that we had last time. Now let's look at the example. So suppose we want to verify associative axiom for multiplication. Okay, so what's the associative axiom for multiplication? It's x times y times z is equal to x times y times z. And let's do it with in the following example. So in example where we take x to be 4, y to be 5, and z to be 6, all mod 7. Right? So let's do the left-hand side. Right? So in this case, so if we have, so in the left-hand side, we have, so what is y times z? So y times z is 5 times 6. So 5 times 6 is 30. So we subtract 28, which is a multiple of 7. So we get 2 mod 7. Right? And what is x times yz? So we have 4 times 2. So that is 8. And so the remainder is 1, mod 7. Right? So now let's do the right-hand side. So in the right-hand side, we have, so x times y. So this is 4 times 5. So that is 20, which is, we subtract 14, so we get 6 mod 7. And then at the end, we get, we need to multiply this by z. So we get 6 times 6. So this is 36. And the result is equal to 1, because we subtract 35, mod 7. So indeed, so the equality holds, right? So we see that we get the same result in the left-hand side and in the right-hand side. So we, in both cases, we got the result of 1. But it is absolutely not clear why this is going to work, right? So because here we got 4 times 2 turned out to be equal to 6 times 6. So this is a little bit of a mystery. Why did this all happen? And it's not absolutely clear to justify, right? So unless we do explicit calculations. So it is not at all obvious that the result of the computation in the left-hand side will be the same as the result of the computation on the right-hand side. Now, let us try to repeat the same example, but now using the new rule. So what will happen here? With the new rule, when we evaluate the left-hand side, so which is x times y times z, so this will be, so our x is 4 times, and y times z is equal to 2. But instead of using 2, what I'm going to do is I'm going to use 30, because here, using this rule, I'm allowed to use any integer with the remainder of 2. And 30 has a remainder of 2. And so this means that the left-hand side is going to be 4 times 30. And the right-hand side is going to be x times y times z. So this is, so x times y is equal to 6, but I can also use 20, right? And I can write it as 20 times z, which is 6. And so then the new rule says that, so we take the remainder, in one case, we take the remainder of 4 times 30, and in the other case, we can take the remainder of 2 times 6. But what is here? So we have 30 is our 5 times 6. And 20 is 4 times 5. And so here it's clear that the integer in the right-hand side is exactly the same as the integer in the left-hand side, because we know that associative law holds for the integers. So this means that the remainder after division by 7 of the right-hand side is going to be the remainder of after division by 7 of the left-hand side, right? And so we can clearly see that 4 times 5 times 6 is the same as 4 times 5 times 6 as an integer, but also as a remainder after division by 7. So this means that whereas with our old rule, verifying the axioms of the field is going to be rather painful and not at all obvious. So with the new rule, So this verification becomes redundant because we simply know that except for the axiom involving inversion, all other axioms hold for the integers. And thus, if we adopt this new rule, then automatically this will hold for the remainders as well. When we switch from the old rule to the new rule, there is a price to pay. So the advantage of the old rule is that it was straightforward. It told us exactly what to do. So just take these remainders, multiply them, and take remainder of the result. The new rule is more ambiguous. It says, take any integers, any pair of integers with prescribed remainders, and multiply them and take the remainder of the result. So there is a danger hidden in this rule. So because this rule may be not well defined. So a priori, it could happen that with one pair of the integers that we take, we get one result. And with another pair, with the same remainders, we could potentially get a different result at the end. And so what we need to do is we need to verify that this rule is indeed well defined. So here, well defined means that so we need to check that the answer does not depend on the pair of integers we pick. Let us state this as a lemma. So lemma, if A1 has the same as remainder as A2 after division by m, right? So we write A1 is equal to A2 mod m. So this means that the integers A1 and A2 have the same remainder after division by m. And B1 has the same remainder as B2 mod m. Then 1. A1 plus B1 has the same remainder as A2 plus B2 mod m. And 2, A1 times B1 is equal to A2 times B2 mod m. So this exactly means that our rule is well defined, so that it wouldn't matter which pair of integers we pick, as long as they have prescribed remainders, then the final result of the computation is going to be the same, both for addition and for multiplication. So let's give the proof of this lemma. So proof. So we recall that having the same remainder means that the difference between the two numbers is divisible by m. So we can write that A1 minus A2 is divisible by m. So this means that this is m times some number k. And the same, so B1 and B2 have the same remainder after division by m. So this means that B1 minus B2 is also a multiple of m. So it's m times s. Now, what we need to show in 1, that A1 plus B1 has the same remainder as A2 plus B2 mod M. And again, we do the same trick. We take the difference between these two integers, and we want to show that this difference is divisible by M. So let's take A1 plus B1 minus A2 plus B2. So that equals. So this is A1 minus A2 plus B1 minus B2. And A1 minus A2 is a multiple of M. It's M times K. And B1 minus B2 is also a multiple of M. So this is M times S. And this is M times K plus S. And what we see is that this is a multiple of M. And the conclusion here is that these two integers have the same remainder after division by M, because the difference is divisible by M. So the conclusion is that A1 plus B1 has the same remainder as A2 plus B2 mod M. Next, let us do a computation for part 2. So in this case, we need to operate with products. So what we need to show, is that the difference between A1 times B1 and A2 times B2 is a multiple of M. So let's take this difference. So A1 times B1 minus A2 times B2. So there is a little trick that we do. So we write this as A1 times B1 minus A1 times B2 plus A1 times B2 minus A2 times B2. So what I did is I took the original expression and then added and subtracted two terms that cancel out. So this means that this whole expression is not changed. But now, here I can write that the first one is A1 times B1 minus B2. And the second one is A1 minus A2 times B2. And then we get that this is A1 times M times S plus M times K times B2. And so this is M times A1S plus B2K. But this has a factor of M, so this is a multiple of M. And so what we did is we verified that A1 times B1 minus A2 times B2 is a multiple of M. And so this means that these two products have the same remainder after division by M. So it doesn't really matter whether we pick a pair A1 B1 or a pair A2 B2. So the final answer of the computation with remainders will be the same. So this lemma allows us to make the following conclusion. That the set of remainders Zm has a well-defined operations of addition, multiplication, and actually we can add to this unary minus. Right, so we saw how to compute the opposites of remainders. And all axioms of the field are satisfied except possibly the axiom of inverse, because we have not discussed yet inverses of remainders. And these axioms are satisfied simply because they are satisfied in Z. So because these axioms hold in integers Z. And so what we saw is that when we verify, say, one of the axioms in Zm, what we can do is we can carry out the computation of the left-hand side and the right-hand side in Z, and then take the remainder only at the last step. And because these axioms, except for the axiom of inverse, all hold in Z, so the result of this computation will be the same for the left-hand side and for the right-hand side. And so now it's the inverse is the sticky part, right? So we have to figure out when is the axiom of inverse hold in Zm. In other words, we need to verify when Zm is a field. So here is our main theorem. Zm is a field if and only if m is a prime number. So what we're saying here is that when m is a prime number, then Zm is a field. When m is not a prime number, then Zm is not a field. Now, the emphasis in this course is on proofs. And so in addition to learning some facts from algebra, we're going to also use the methods of proving things. So now let us discuss a strategy for proving a statement like this. So what we have here is we have two statements. A and B. So in our case here, A is a statement that Zm is a field, and B is a statement that m is a prime number. Both A and B potentially could be true or false. Then to say A holds if and only if B holds. So symbolically, we're going to write this in the following way. A, if and only if B. So this is the sign for logical equivalence. Or if and only if. Now, there are two strategies for proving this. So the first strategy is the following. We can prove that if A holds, then B holds. And also prove that if B holds, then A holds. So if we prove these two facts, then this would mean that A and B are logically equivalent. Now, there is a second strategy for proving exactly the same thing. So what we can do instead is we can prove that if A holds, then B holds. And if A fails, then B fails. So these are two different methods of proving logical equivalence of statements A and B. And when we prove this theorem, right, so here we need to prove that Zm is a field if and only if M is a prime number. So actually, so we're going to follow the second strategy, but maybe with A and B switched. So what we're going to do is to prove the following pair of claims. So we need to show A. If M is a prime number, then Zm is a field. And B, if M is not a prime number, then Zm is not a field. The second part is easier to show. Let's first start with an example. Let's take M equals 6. So 6 is a composite number, so this is not a prime. So perhaps let's recall what's the definition of a prime. So M is a prime if it is divisible only by 1 and itself. And 6 is not a prime because it's divisible by 2 and by 3. So let's look at Z6. So the remainders in Z6 go from 0 to 5. So what do we know? So we know that here we have well-defined addition, multiplication, and unary minus. Now the point here is that we need to see if there is inversion in Z6. So let us explore multiplication in Z6. So let us take 2 and multiply it by 3. So what is the result of the calculation? 2 times 3 is 6, but the remainder of this is 0. So what we see here is that 2 is not equal to 0 mod 6. And 3 is not equal to 0 mod 6. But 2 times 3 is equal to 0 mod 6. So this means that 2 and 3 are divisors of 0 in Z6. And the conclusion is that Z6 is not a field. Because we have our mantra that says that any field cannot have divisors of 0. And so the fact that 2 and 3 are divisors of 0 in Z6, this indicates that Z6 is not a field. And this also indicates that 2 and 3 are not invertible in Z6. And indeed, so we cannot find a solution to the equation 2x is equal to 1 mod 6. Or we cannot find the solution for equation 3x is equal to 1 mod 6. This example can be easily generalized to give us the proof of part B. So now we can easily show that if M is not a prime number, then Zm is not a field. Let us write down a formal proof of this. So proof of part B. So assume that M is not a prime number. Then M is composite. So we can write M as K times S, where both K and S are strictly greater than 1 and less than M. Then consider K times S mod M. But this is the same as M mod M. Right? So because K times S is equal to M. And thus this is equal to 0 mod M. But both K and S are less than M. So this means, and they are greater than 0. So this means that K is not equal to 0 mod M, and S is not equal to 0 mod M. And we conclude that K and S are divisors of 0 in Zm. Hence, Zm is not a field. And we completed the proof of part B. So we proved that if M is not a prime, then Zm is not a field. In order to give the proof of part A, we need to develop additional theory that will allow us to compute inverses in Zm when M is a prime. We will come back to complete the proof of our theorem, but now let us discuss Euclidean algorithm for greatest common divisor. Now, we want to find the greatest common divisor of two integers. So let's look at an example. So suppose we need to compute GCD, greatest common divisor, of 84 and 48. Now, what is the high school method? So one method is says, well, factor these numbers into powers of primes. So let's take 84. So what factors do we have here? So this is 2 times 42. So which is 2 times 2 times 21. This is 2 times 2 times 3 times 7. And what is 48? 48 is 2 times 24, which is 2 times 2 times 12, which is 2 times 2 times 2 times 6, which is 2 times 2 times 2 times 2 times 3, right? And now we look at these prime expansions of these two numbers, and we pick the greatest common part of these factors. So what we can see is here the common part will be 2 times 2 times 3. And so this means that the greatest common divisor of these two numbers is equal to 12, which is 2 times 2 times 3. Unfortunately, this method does not work well with large integers. Say, if I ask you, what is the greatest common divisor of the following two numbers? All right. So here, that's become harder, right? So because one would have to try to factor these numbers into primes. And this is a notoriously difficult problem. In fact, the problem of factorization, so factorization of large integers into primes, into a product of primes, is hard. So this is a difficult problem, and in fact it's a basis for RSA cryptosystem. So this means that you can build encryption of data using factorizations of large numbers into primes, and the fact that even with computers it is really difficult to factor integers into primes. However, finding greatest common divisors, even for very large integers, is extremely easy with a computer. But we have to use a different method. So this method of factorization does not work at all for large integers. And instead, one can use an algorithm which is due to Euclid. So well before the advent of computers, Euclid figured out how to compute greatest common divisors of even very large integers in a computationally tractable way, so that with computers we can compute greatest common divisors of very large integers without being able to factor them. The Euclidean algorithm is based on the following lemma. So let A and B be a pair of integers. And let's assume that A is greater or equal to b. So then divide a by b with the remainder. So this means that we write a as b times k plus a remainder r, where r is between 0 and it's strictly less than b, because we're dividing by b. So then the claim that GCD of a and b is equal to the GCD of b and r. And this is a beautiful fact, because now, so the pair of integers b and r is smaller than the original pair a and b. And we can relate the question of finding greatest common divisors of a larger pair to the question of finding the greatest common divisor of a smaller pair. But then we are going to iterate this idea. So when we compute GCD of b and r, so we are going to do the same step. So we are going to, well, r is less than b. So now we are going to take b and divide it by r with the remainder. And so on and so on and so on. Now, let's do an example. So let's take the same integers 84 and 48 and compute their GCD using Euclidean algorithm. All right, so what we have to do is, so this tells us that we need to take 84 and divide it by 48 with the remainder. So this is going to be 1 times 48 plus, so how much is left? Plus 36. And so this will tell us that this GCD is equal to GCD of 48 and 36. Now we take 48 and divide it by 36 with the remainder. So we write 48 is 1 times 36 plus 12. So then, iterating this lemma, this tells us that this is also equal to GCD of 36 and 12. Next, we do it again. So we have 36 is equal to 3 times 12 plus 0. So this 0 indicates that 36 is actually divisible by 12. And at this point, this algorithm will terminate, because now we've got that 36 is divisible by 12, so clearly the greatest common divisor of 36 and 12 is 12. And by this lemma, so we go back and we conclude that the greatest common divisor of 84 and 48 is also 12. Let us give the proof of this lemma. So let us show that common divisors of a pair AB are the same as common divisors of the pair B and R. Right? So if we show that common divisors of this pair are the same as common divisors of this pair, then clearly the greatest common divisor of this pair is equal to the greatest common divisor of this pair. Now, let D be a common divisor of the pair AB. So this means that A is a multiple of D. A is D times S, and B is also a multiple of D. So D times N. Now, we have that R is the remainder of A after division by B. So A is B times K plus R. So then R is A minus BK. But A is ds, so we have ds. Minus B is dn, d times n times k. And so this is d times s minus nk. So what we see is, we see that d is a divisor of R, but also D is a divisor of B. So what we showed, so what we have shown here is that any common divisor of the pair AB is a common divisor of the pair BR. So now we see that every common divisor of AB is a common divisor of BR. And I leave it as an exercise for you to show that every common divisor of BR is a common divisor of AB. And then we would get the conclusion that common divisors of pair AB are the same as common divisors of the pair BR, and as a result, greatest common divisor of this pair is the same as the greatest common divisor of this pair. And now we proved that Euclidean algorithm works. With the help of Euclidean algorithm, we can prove the following theorem. Let D be the greatest common divisor of A and B. Then there exist integers U and V such that D is equal to A times U plus B times V. Now, this is not obvious at all. So let's look at an example. So what's the greatest common divisor, say, of 53 and 37? Well, 37 is a prime number, and 53 also, right? So this means that this is surely is equal to 1. Now, what this theorem claims is, so here A is 53, B is 37, and 1 is the greatest common divisor, so this is D. So this theorem says that we can write 1 as 53 times U plus 37 times V, where U and V are integers. Now, clearly, one of these have to be positive and one has to be negative. But what are the values of these integers? Well, I don't know, right? So trying to guess the values of u and v is rather challenging. But the nice thing is that we can calculate the values of u and v using a version of Euclidean algorithm, which is called extended Euclidean algorithm. Let's do it. So we begin by computing the greatest common divisor of 53 and 37 using Euclidean algorithm. We know the answer, so the answer is going to be 1. But nonetheless, what we are interested in is in the way how Euclidean algorithm arrives to this answer. So we start with 53, and we divide it by 37 with the remainder. So 53 is equal to 37, plus the remainder is going to be 16. So then we divide 37 by 16 with the remainder. So we write 37 is 2 times 16, so which is 32, plus a remainder, which is 5. Next, we have to take 16 and divide it by 5 with the remainder. So we write down 16 is 3 times 5 plus 1. Now, at the end of the day, so this tells us that GCD of 53 and 37 is the same as the GCD. Well, our last pair is going to be 5 and 1, which is 1, because 5, well, anything is divisible by 1. So this means that if we get 1 as our remainder, then this means that 1 is going to be the value of the GCD. Now, what we're going to do next is now we're going to put this calculation in reverse. So we're going to start with this 1 here. And we're going to write 1 as 16 minus 3 times 5. Well, that's true. 16 minus 3 times 5 is equal to 1. So then we go and go up in this chain of equalities. So here we can write down 5 as 37 minus 2 times 16. So we get 16 minus 3 times, instead of writing 5, we'll write down 37 minus 2 times 16. Now, if we expand this, we get 16 minus 3 times 37 and plus, so 3 times 2 is 6 times 16. So this tells us that we get 16 and 6 times 16. So this can be written as 7 times 16 minus 3 times 37. So now we're saying that 1 is also equal to 7 times 16 minus 3 times 37. Now this is not so obvious anymore, but let's check. So here we get 70 plus 42. So this is, so this number is 112. And 3 times 37, that's 90 plus 21, that's 111. Okay, so this works out. So we have 1 is 112 minus 111. So far, so good. So next, we climb up in our chain of equalities, and we can write 16 as 53 minus 37. So here we're going to get is 7 times 53 minus 37 minus 3 times 37. And so that is 7 times 53 minus 7 times 37 and minus 3 times 37. So that becomes 7 times 53 minus 10 times 37. And this gives us the answer for the values of u and v. So this tells us that u here can be taken as 7 and v can be taken as negative 10. Right? Okay, let's check. What is 53 times 7? So this is 350 plus 21, 371. Minus 37 times 10 is 370. All right, so now we found u and v such that 1 is 53 times u plus 37v. To reinforce our understanding of extended Euclidean algorithm, let us solve the following problem. Compute d, the greatest common divisor of 126 and 78, and express it as in the theorem. D equals 126 times u plus 78 times v. So we need to find integers u and v that satisfy this property. So we begin with the standard part of Euclidean algorithm. So this means that we start by dividing 126 by 78 with the remainder. So we have 126 is equal to 78 plus 48. Then we divide 78 by 48 with the remainder. So we have 78 is 48 plus 30. We divide 48 by 30 with the remainder. 48 is 30 plus 18. Next, we divide 30 by 18 with the remainder. So we have 30 is 18 plus 12. And then we divide 18 by 12 with the remainder. So we have 18 is 12 plus 6. And now we see that the GCD of 12 and 6 is equal to 6 because 12 is divisible by 6. And so we conclude from here that D is equal to 6. So now we need to find u and v such that 6 is equal to 126 times u plus 78 times v. And we run the extended part of Euclidean algorithm. So this means that we start with the last equality where 6 was in the remainder and move up. So we have 6 is written as 18 minus 12. That's true. So then we express 12 as 30 minus 18. So we get 18 minus 30 plus 18. So this is 2 times 18 minus 30. So next we climb to 18 and we need to eliminate 18 as 48 minus 30. So this is 2 times 48 minus 30 minus 30. If we expand this, we get 2 times 48 minus well, have 2 times 30 and minus 30, so that's 3 times 30. Then we eliminate 30 as 78 minus 48. So this is 2 times 48 minus 3 times 78 times 40 minus 48. So that becomes 2 times 48 minus 3 times 78 plus 3 times 48. So which is 5 times 48 minus 3 times 78. And finally, we eliminate 48 from here. So it's writing 48 is 126 minus 78. So we get 5 times 126 minus 78 minus 3 times 78. So that is 5 times 126 minus 5 times 78 minus 3 times 78. So which is 5 times 126 minus 8 times 78. And our conclusion is that u is equal to 5 and v is equal to negative 8. And one can check that 126 times 5 minus 78 times 8 must be equal to 6. Now, what we see here is that we have an algorithm to compute or to represent the greatest common divisor d as a times u plus b times v, which is due to the extended Euclidean algorithm. And this gives us the proof of this theorem, simply because we have the algorithm for finding such a presentation. Using this theorem, now we can complete the proof of our result about Zm. So this is part A that was remaining. If M is a prime, then Zm is a field. Let's give a proof of this. Assume M is a prime number. We need to show that every non-zero remainder B mod M has a multiplicative inverse. Now, let us consider greatest common divisor of M and B. Now, what would it be? M is a prime number, so its divisors are 1 and M. And B is a non-zero remainder, so this means that B is not divisible by M. So this tells us that the only common divisor of these two integers is 1. So the greatest common divisor of M and B is equal to 1 because M is prime and B is not divisible by M. Now let's apply the previous theorem. So by previous theorem, there exist integers u and v such that d, which is 1, is equal to m times u plus b times v. Now let's take this equality and let's take the remainder mod m of both sides. Well, the remainder of 1 is still 1. Now here, the first term is a multiple of m. So this means that the remainder of m times u is equal to 0. And so then we have just b times v mod m. And this is equal to b times v mod m. So this tells us that b times v is equal to 1 mod m, which means that v is the inverse, multiplicative inverse of b in Zm. Because, well, since these two multiply to 1, this means that they are multiplicative inverses of each other. And we conclude that b is invertible in Zm. So we proved that every non-zero remainder in Zm has a multiplicative inverse. So this tells us that Zm is a field. I will ask you to do the following exercise. Show that a remainder b is invertible in Zm if and only if greatest common divisor of m and b is equal to 1. So, for example, in Z35, remainder 8 is invertible, but 10 is not. And to complete today's lecture, let's do the following problem. Find 10 inverse in Z37. Well, 37 is a prime number, so in Z37, every non-zero remainder has a multiplicative inverse. So let's find the multiplicative inverse of 10. So this means that we are solving the equation 10 times x is equal to 1 mod 37. So to do this, we have to calculate the GCD of 37 and 10 using Euclidean algorithm. We actually know that this is going to be 1 because 37 is a prime number. But we need the calculation. So 37, so we divide it by 10 with the remainder. So this is 3 times 10 plus 7. Then we take 10 and divide by 7 with the remainder. 10 is 7 plus 3. And then we take 7 and divide by 3 with the remainder. 7 is 2 times 3 plus 1. And 1 is the GCD that we seek. So this means that now we arrived to the end of this calculation. And now we have to do the reverse part of it. So we start and work out backwards. So 1 is 7 minus 2 times 3. Then we eliminate 3. So we get 7 minus 2 times 10 minus 7. So this is going to be 3 times 7 minus 2 times 10. Okay, that's 21 minus 20. Works. So then we eliminate 7. So this is 3 times 37 minus 3 times 10 and minus 2 times 10. So that is 3 times 37 minus 9 times 10 minus 2 times 10. So this is 3 times 37 minus 11 times 10. So we get the following equality. So now we got that 1 is equal to 3 times 37 minus 11 times 10. So this is an equality in integers. So this is 111 minus 110 is equal to 1. So we need the equality of remainders. So now we take the remainder of both sides after division by 37. So here we have 1 on the left, right? So the remainder of 1 is 1. Now, here we have a multiple of 37. So this means that the remainder of this is going to be 0 minus 11 times 10. Now this is mod 37. So this tells us that 1 is negative 11 times 10, mod 37. And this tells us that the multiplicative inverse of 10 is equal to negative 11 in Z37. But what is negative 11? So negative 11 is the same thing as 37 minus 11. And this is equal to 26. So our conclusion is that 10 inverse is equal to 26. Or 10 times 26 is equal to 1 mod 37.